In the unending silence of the void, where distances are measured in light years and time is counted in eons, humanity has always cast its gaze upward, asking the two most profound questions that can be conceived. Where did all of this come from? And from that vast cosmic tapestry, where did we come from? For generations, our answers were confined to mythology, to philosophy, and then to the glimmers of light captured by our telescopes. We built greater and greater eyes, each one peeling back another layer of the cosmic onion, each revealing a universe more ancient and more magnificent than the last. We thought we were closing in on the story of our genesis. We had a timeline, a sequence of events, a grand narrative of cosmic evolution. It was a story of patience. A universe born in fire, cooling in darkness, and then, slowly, painstakingly, over hundreds of millions of years, igniting its first stars, and then gradually assembling its first fledgling galaxies. It was a story that made sense. It was orderly, but it may have been entirely wrong. Out beyond the orbit of the Moon, a million miles from Earth, drifts a creation of pure genius, an instrument of impossible precision. Its gaze is fixed not on the familiar stars of our night, but on the darkness between them. It is a time machine, its segmented golden eye collecting photons that have been traveling since the dawn of the universe itself. This is the James Webb Space Telescope, and in the silent flood of data it sends back to Earth, it is not just confirming our story of creation, it is tearing the pages out of the book and forcing us to start anew. The images it has captured, from the very edge of observable reality, show us something that shouldn't exist, something that defies the laws of cosmic growth as we have written them. Did this revolutionary observatory just stumble upon the true origin of our cosmic home, and in doing so, has it forever altered the story of us? To comprehend the revolution that is now unfolding, we must first understand the journey that brought us here. Our quest to see the beginning of time is a story of light. For centuries, we were explorers confined to a single, narrow shoreline of the electromagnetic ocean, the sliver of visible light our eyes evolved to perceive. Galileo's first spyglass revealed the moons of Jupiter, shattering the celestial spheres of antiquity. Larger and more sophisticated instruments followed, painting a portrait of a universe filled with immense, swirling islands of stars we named galaxies. Then came the Hubble Space Telescope, a triumph of human ambition launched above the blurring distortion of Earth's atmosphere. Hubble showed us galactic collisions, the birth of stars in stellar nurseries, and the faint, ghostly smudges of galaxies billions of light years away. It took us deep into cosmic history, producing images that transcended science and became cultural icons of our place in the cosmos. But Hubble, for all its power, had a fundamental limitation. It was, for the most part, an eye that saw as we do, in visible and ultraviolet light, and when you are trying to see the very first objects in the universe, that type of vision is like trying to see through a dense, impenetrable fog. The universe is expanding. This is the foundational discovery of modern cosmology. Every galaxy is rushing away from every other galaxy, a concept that rewinds to a single, infinitely dense point in the past, the Big Bang. This expansion has a profound consequence for the light that travels through it. Imagine a beam of light as a perfectly rhythmic wave. As this wave journeys across billions of years of stretching space-time, the wave itself is pulled, elongated, its frequency lowered. Light that began its existence as brilliant, high-energy blue or even ultraviolet light is stretched down the spectrum, through the yellows and oranges, and finally into the long, cool wavelengths of infrared. This phenomenon is called cosmological redshift. The farther away an object is, the faster it recedes, and the more its light is redshifted. The very first stars and galaxies, burning at the dawn of time, sent forth a torrent of brilliant, visible light. But after traveling for over 13.5 billion years to reach us, that primordial radiance has been stretched into invisibility. It has become a faint, thermal glow, a whisper in the infrared. Hubble could not perceive it. To see the cosmic dawn, we needed a different kind of eye. We needed a machine that could capture this ancient, spectral ghost. Building such an observatory was one of the greatest technological challenges humanity has ever undertaken. The James Webb Space Telescope is not merely a successor to Hubble. It is a different species of instrument altogether. Its primary mirror is a breathtaking mosaic of 18 hexagonal segments of beryllium, each coated in a microscopically thin layer of pure gold, an element chosen specifically for its supreme ability to reflect infrared light. When unfolded in space, this mirror spans over 6.5 meters, a giant, light-collecting bucket designed to catch the faintest, oldest photons in existence. The precision required is difficult to articulate. Each of the 18 segments must be aligned to within a fraction of the width of a human hair, working in perfect concert to form a single, flawless parabolic surface. This is a level of accuracy akin to scaling the entire mirror up to the size of a continent, and having no imperfection larger than a few inches. But even this magnificent mirror would be useless without another, equally audacious feat of engineering. Infrared is heat. The telescope itself, if warm, would glow with its own infrared light, blinding its sensitive instruments and drowning out the faint signals from the edge of time. To see the cold universe, the telescope must be colder still. It must operate at a temperature of just a few tens of degrees above absolute zero, that theoretical point where all atomic motion ceases. To achieve this, JWST is shielded by a colossal 5-layered sunshield. The size of a tennis court, this structure of gossamer-thin, reflective kapton acts as a giant parasol, constantly positioned between the telescope and the sun, earth, and moon. Each successive layer is cooler than the one before it, reflecting and radiating heat into space until the observatory on the dark side is plunged into a profound, cryogenic cold. This is the machine we sent to hunt for our origins. A golden eye, chilled to the verge of absolute zero, designed to capture the last echoes of the universe's first morning. And when that eye finally opened, what it saw sent shockwaves through the world of astronomy. The established narrative of the early universe was one of slow, majestic assembly. Following the Big Bang, the cosmos was a roiling, opaque soup of elementary particles. For nearly 400,000 years, it was too hot for atoms to form. Light was trapped, scattering endlessly off free electrons. Then came a moment of transition known as recombination. The universe cooled enough for protons and electrons to combine into neutral hydrogen atoms. Suddenly, light was free to travel. This is the origin of the cosmic microwave background, the afterglow of creation itself. But this release of light also plunged the universe into a period known as the Cosmic Dark Ages. There were no stars, there were no galaxies. There was only the primordial hydrogen and helium gas, drifting in near total blackness, governed only by the gentle, persistent pull of gravity. Our models, built on decades of observation and theory, painted a clear picture of what happened next. In the densest regions of this cosmic gas, gravity began to win. Clumps formed, slowly pulling in more and more material. After perhaps 100 or 200 million years of this gradual accumulation, the core of the largest clumps would become dense and hot enough to ignite nuclear fusion. These were the first stars, the so-called population 3 stars. They were unlike anything that exists today. Forged from pure hydrogen and helium, they were gargantuan, hundreds of times the mass of our sun, burning with an almost unimaginable ferocity. They lived fast and died young, exploding as supernovae after only a few million years. But in their explosive deaths, they performed a vital act of creation. For the first time, they forged heavier elements, carbon, oxygen, silicon, iron, and seeded the surrounding gas clouds with them. From these enriched clouds, the next generation of stars would form, and these stars, grouped together in small clusters, would represent the seeds of the first galaxies. The prevailing theory was a bottom-up model of cosmic construction. Small irregular dwarf galaxies would form first. Over hundreds of millions, even billions of years, these smaller structures would collide and merge. gradually building up into larger, more organized, spiral and elliptical galaxies, like our own Milky Way. It was a story of cosmic patience, of construction happening one brick at a time. This is what astronomers expected to see when JWST peered into the abyss. They anticipated finding faint, messy, barely formed proto-galaxies, the humble beginnings of the grand structures we see today. The first JWST deep field images were released to a waiting world. They were jewels scattered on black velvet, a window deeper into space and time than ever before. Every smudge of light in the image was a galaxy. But as scientists began to analyze the faintest, reddest, and therefore oldest objects, a profound sense of confusion and then astonishment began to spread. The infant galaxies were not what they were supposed to be. They were not small, clumpy, and chaotic. Among the oldest candidates, objects whose light had traveled for over 13.4 billion years, dating back to just 300 to 400 million years after the Big Bang, were galaxies that were shockingly massive. Some appeared to have stellar populations rivaling that of the modern Milky Way. They were also surprisingly well structured. Some even showed evidence of spiral arms or galactic disks, features that were thought to take billions of years of cosmic evolution to develop. The discovery was analogous to an archaeologist excavating a site from the early Stone Age, expecting to find primitive hand axes and crude shelters, but instead unearthing the foundations of a skyscraper. It simply didn't fit the timeline. The universe, it seemed, was in a hurry. It had gone from darkness to sprawling, mature cities of stars, in a fraction of the time our best models had allocated. These objects were nicknamed universe breakers because their very existence threatened to shatter our understanding of cosmic formation. How could the universe build something so big, so quickly? The slow, steady, bottom-up model of gradual mergers couldn't account for this accelerated timeline. It would be like trying to build a modern metropolis in a single decade using only hand tools. There simply wasn't enough time, and the available resources, the primordial gas, couldn't be gathered and converted into stars that rapidly through gravity alone. A new ingredient was needed, a new mechanism for super-fast construction. Scientists scrambled to find an explanation. Perhaps these objects weren't as far away as they seemed. Maybe their extreme redness was caused by something else, like immense amounts of interstellar dust. But as JWST's powerful spectrographs went to work, dissecting the light from these enigmatic galaxies, the data was confirmed. Their redshifts were enormous. They were indeed relics from the cosmic dawn. The problem was real. Our story of origins was missing a critical chapter. And the most compelling, most audacious explanation points to the most mysterious objects in the cosmos. Supermassive black holes. Every large galaxy, including our own, has a supermassive black hole at its center. Sagittarius A*, the black hole at the heart of the Milky Way, is more than 4 million times the mass of our Sun. For decades, the assumption was that galaxies and their central black holes grew up together in a process of coevolution. As a galaxy pulled in more gas and merged with other galaxies, it would feed its central black hole, which would grow in lockstep with its host. The galaxy came first, and the black hole was a consequence of its growth. But the impossible early galaxies discovered by JWST have turned this idea on its head. What if the black hole came first? A radical new theory is gaining traction, one that posits the existence of direct collapse black holes. Imagine, in the very early universe, a colossal cloud of pristine hydrogen gas, so massive that it doesn't fragment into myriad stars. Instead, under its own immense gravity, the entire cloud collapses catastrophically, bypassing the star formation phase entirely and falling in on itself to form a black hole tens of thousands, or even hundreds of thousands, of times the mass of the Sun. These would be primordial black hole seeds sown into the fabric of the cosmos. Within the first couple 100 million years, these seeds would be game changers. They would act as potent gravitational anchors, overwhelming the normal, patient process of galaxy formation. Instead of gas clouds slowly coalescing, these massive black holes would create immense gravitational wells, voraciously pulling in gas from vast surrounding regions. They wouldn't just be feeding themselves, they would be creating a hyper-dense environment that would trigger furious explosive bursts of star formation all around them. This wasn't the slow brick-by-brick construction of the old model. This was like setting up a massive, prefabricated gravitational scaffold and having the entire galactic city spring into existence around it almost instantaneously. The black hole wasn't a feature of the galaxy, it was the creative engine. This black hole-first or top-down model could potentially explain the shocking size and maturity of JWST's ancient discoveries. It suggests the universe was born with the seeds of its own grand structures already in place. This fundamental rewriting of galactic history has profound implications for our own origins. It directly impacts the timeline for the creation of the elements essential for life. The Big Bang produced only hydrogen, helium, and trace amounts of lithium. Every other element on the periodic table, the carbon that forms the backbone of our DNA, the oxygen we breathe, the iron in our blood, the silicon in the rocks beneath our feet, was forged in the hearts of stars and scattered throughout the cosmos when they died. We are, as the famous saying goes, made of star stuff. In the old, patient model of galaxy formation, this process of chemical enrichment was also slow. It would take many generations of stars, living and dying over billions of years, to build up a sufficient concentration of these heavier elements, which astronomers call metals. Planets like Earth, which are rocky and rich in metals, could not have formed until the universe was sufficiently seeded. Life, as we know it, which depends on a complex carbon-based chemistry, would have to wait even longer. This placed our own existence relatively late in the cosmic story. But if JWST is correct, if massive galaxies were forming and churning out stars at a furious pace, just a few 100 million years after the Big Bang, then the entire timeline of chemical enrichment is drastically accelerated. These supergalaxies would have been cosmic forges, operating at maximum capacity. Their massive, short-lived stars would have rapidly synthesized vast quantities of heavy elements, and then expelled them in spectacular supernova explosions. The universe may have become metal-rich far earlier than we ever thought possible. The raw ingredients for rocky planets, and perhaps for life itself, may have been widely available when the universe was less than a tenth of its current age. This realization is a profound shift in perspective. JWST isn't just showing us the origin of galaxies, it is showing us the origin of the atoms that make up our world and our bodies. When we look at the light from an object like glass, Z1-3, one of these impossibly early galaxies, we are not just observing a distant astronomical curiosity. We are potentially witnessing the crucible where the very first life-giving elements were synthesized. On a galactic scale, the light from that galaxy began its journey long before our Sun or Earth even existed. It traveled across a constantly expanding void for 13.5 billion years, destined to be collected by a golden mirror and focused onto a detector built by beings whose own atomic ancestors were forged in similar cosmic cauldrons. The Discovery telescopes the vastness of cosmic time, connecting the biochemistry of our own planet directly to the violent, creative frenzy of the universe's earliest youth. This new cosmic narrative forces us to reconsider the timeline for life in the universe. If the ingredients for rocky planets and complex chemistry were present billions of years earlier than we assumed, it dramatically widens the window of opportunity for life to emerge elsewhere. The Copernican principle suggests that Earth is not in a privileged position in the cosmos. If life happened here, it could happen elsewhere under similar conditions. We have always wondered if we were the first. JWST's findings hint that we may, in fact, be relative latecomers to the cosmic stage. It is conceivable that life-bearing planets could have formed around stars in those ancient galaxies, billions of years before our own solar system coalesced from its cloud of gas and dust. It opens up the speculative, but now scientifically grounded, possibility of ancient civilizations that may have risen and fallen before the light from their home galaxies even began its journey toward us. Of course, With every great discovery comes a new set of even deeper questions. If massive black hole seeds are the answer, where did they come from? Does their formation require a new understanding of physics in the extreme environment of the early universe? Or could they be evidence for something even more exotic, like primordial black holes, formed not from collapsing gas, but from density fluctuations in the first seconds after the Big Bang itself? Furthermore, these discoveries are putting immense pressure on our understanding of the universe's invisible components. Dark matter is the mysterious substance that provides the extra gravitational glue, holding galaxies together. Our models of how dark matter should clump together in the early universe helped inform the slow growth model of galaxy formation. The existence of these massive early galaxies might mean our theories about the nature of dark matter itself are incomplete or in need of revision. JWST is just beginning its mission. What we have seen are the first postcards from the edge of time. Each new observation, each new spectrum analyzed, will add another piece to this revolutionary puzzle. Scientists around the world are now engaged in a feverish campaign to confirm the masses and compositions of these ancient systems, to hunt for even older and more distant objects, and to refine their computer simulations to see if they can recreate a universe that builds itself so quickly. The telescope has thrown down a gauntlet to the scientific community, challenging them to abandon old certainties and embrace a cosmos that is proving to be far more dynamic and creative in its infancy than we ever dared to imagine. We stand at a pivotal moment in human history. For millennia, our origin story was rooted in the soil beneath our feet and the myths we told around the fire. Then, science took us on a journey outward, from our planet to our star, from our star to our galaxy, and from our galaxy across the expanding universe, back toward the moment of creation. We built a narrative that seemed to fit the evidence we had. Now, an instrument of our own making, a marvel of glass and gold and cryogenic genius, has looked into the deepest recesses of the past and brought back a new truth. It tells us that the story of structure, the story of chemistry, the story of the potential for life, the story of us began almost as soon as the universe itself was born. We are the descendants of this unexpectedly rapid creation. The atoms within us carry the memory of those first furious stars in those first impossible galaxies. The light that traveled across the immensity of space and time to tell us this story is not foreign. It is the light of our own ancestral home. The James Webb Space Telescope has not given us the final, complete answer to our cosmic origins. Instead, it has done something far more valuable. It has shown us that the universe is more surprising, more mysterious, and more magnificent than we knew. It has shattered our old map and invited us to explore a new, uncharted territory. The cosmic dawn was not a gentle sunrise. It was a brilliant, explosive, and astonishingly rapid conflagration. And in its ancient light, we are, for the first time, beginning to see our own true beginning.